Hello everybody, so this is the second video for chapter 5 of the reinforcement learning course. In the first video for this chapter, we introduced our first class of reinforcement learning algorithms in the context of Markov decision processes to optimize the objective function or the expected discounted reward of some agent. So the family of algorithms we've discussed or introduced is Monte-Carlo algorithms, where we can simulate episodes of the Markov decision process, calculate rewards and returns, and estimate the value function for a given state as the average of all returns which were obtained starting from that state S. Okay, so the last chapter mainly until estimating the value function for a given policy, so policy evaluation. Um, and which value function was the state value function. Okay, so now in this video we're going to extend this idea now to action value functions instead of state value functions. And furthermore, by the end of the video, we're going to discuss what we call the control problem, where instead of considering a fixed policy, we will show how to progressively refine our estimate of the optimal policy. Okay, so in the previous chapter, chapter 4, we discussed dynamic programming algorithms, and we saw that there existed some relationship between the action value function of a policy and the state value function. Okay, so we saw this relationship here where the action value function for a policy pi was obtained by summing all possible next states and rewards across all possible next states and rewards. The transition probability of getting into these new states and rewards times the next reward plus the discount factor times the state value function in the next step. Okay, so in the first part of the video, we showed how to estimate this v pi here, the state value function. So does this mean we can automatically get the action value function? The answer is no, because if we wanted to rely on this, well, the problem is this part here. Okay, so in many problems, the transition function is not observable, is not known. So for this reason, it's not automatic to obtain an estimate of the action value function if we know the state value function. Okay, so we need an algorithm to estimate directly the action value function if we need that function. And why do we need that function? It's because if we want to refine our policy, so let's say we start with a policy and we want to refine it, we saw in the previous chapter that the policy improvement procedure relied on this action value function here. Okay, so to build a new policy which was better than the previous one, you had to compare the value of all actions in that state S and pick the best action. So to do policy improvement, getting these action value functions is very important. So we will need to discuss how to estimate this action value function. So as we said, we're gonna consider the problem of estimating this action value function with Monte-Carlo algorithms. Okay, we're gonna use similar ideas to what we did in the earlier part of the chapter. Okay, so here, just a quick recall, Q pi S is the expected return. So return is the sum of future discounted rewards. If we start in state S, perform action A in state S, and then for all subsequent actions, we follow the policy pi. Okay, so this is the definition of Q pi S. So we'll want to estimate that quantity with Monte-Carlo methods. Okay. So again, with Monte-Carlo methods, the idea we're going to pursue is we will simulate many episodes of the Markov decision process And then we'll look at all episodes where, uh, let's say we want to estimate the value function for a state pair SA. We're going to look at all episodes and see in which of them there was the action A taken in state S. And then every time we find such a situation, such outcome, then we're going to look at the return which was obtained after visiting that state action pair SA, and average all such returns to obtain estimates of the action value function. Okay, so similar to what we had previously, there are two methods that we can consider, which is the first visit method and the every visit method. Okay, so again, in both these methods, we simulate multiple episodes of the Markov decision process following some policy pi. And then what we do in the first visit method, we only consider the first visit to the state action pair SA within the episodes, and all other visits in the same episode to that same state action pair, we just disregard them. Okay, so in the first visit MC method, we look at all paths. For paths where the state action pair was never visited, SA was never visited, we just discard the paths. And for all paths, or sorry, when I say paths, I mean episodes. For all episodes in which the state action pair SA was visited, meaning that action A was taken at some point in state S, then we take the first time in the episode this outcome occur, we look at the associated return, and then we do that for all episodes and average all such returns associated with the state action pair SA. Okay, so first visit only considers the first visit to SA in a given episode, whereas the every visit method, you for a given episode, let's say that state action pair was visited multiple times, then you'll consider all all returns associated with these state action pairs, and you'll, even after simulating many episodes, you'll average all such returns, okay, for all visits across the episodes of the state action pair SA. Okay, so again, proofs are omitted, but these methods, they provide estimates which will converge to the true value with probability 1. So this is the law of large numbers, and the standard error of this estimate is proportional to 1 over square root of n, where n is the number of visits to the state action pair SA. Okay, so in the first visit Monte-Carlo method, this is again very obvious because all such returns are IID, because the various episodes are independent, whereas in the every visit method, there's some dependence between the returns if they come from the same episode. So let's say state action pair SA was visited multiple times in an episode, then the various returns in this episode will of course be dependent. But again, we can invoke milder versions of the strong law of large number and still have obtained convergence. Okay, so mathematical details are omitted, but this is the main idea and main outcome for these algorithms. Okay, so is this a good way of proceeding? This is the first approach proposed in the book, but what's going to happen, or what might happen, is that some state action pairs might never be visited if you do that. Okay, so if across all your episodes, then you never took action A in state S, this means that you have no no returns associated with that state action pair to average so as to estimate the function Q evaluated in SA. Okay, the action value function. So because you just have no returns to average, the estimate for that state action pair is just unavailable. Okay, so we can see that this will happen systematically if you have a deterministic policy. Okay, so let's say pi is a deterministic policy, which means that in any state S, there's a single action that is taken by that policy. All other actions are associated with a probability 0. So if for all states S there exists an action called pi S which is systematically selected, then you'll never have estimates for the value of other actions in that state S. Okay, so all state action pairs SA where the action is different from the one selected by the deterministic policy, they'll never be visited and it won't be possible to estimate your action value function q pi in that state action pair SA. Okay, so this is a serious problem because, as we said, if you want to do some policy improvement, you need to have estimates for the value of all the actions, not only for the action selected by your current policy. Okay, so how do we remedy that problem? Well, this shows that we need to have constant exploration. Okay, so if we want to use Monte-Carlo algorithms to estimate the action value function, it means that we must explore at some point all possible state action pairs, which means that in a given state S, every action should be sometimes selected with at least a small probability. Okay, so to ensure that all possible state action pairs occur. So we'll first present one approach to do that, which is called exploring starts. But in practice, we're going to see that this method is not good. Okay, so unless you have very small problems, this method might not work very well. However, it's convenient to understand. Okay, so although in practice it might not be the best idea, it's very useful to understand what is happening. Okay, so and then we're gonna see other approaches more convenient in practice in the rest of this chapter. Okay, so this exploring start approach, which can remedy the problem we've just discussed, consists in doing the following. Okay, so with exploring starts, what you do is every time you start a new episode, you impose that the initial state of this episode is randomly selected, and then the first action in that state is also randomly selected, with all possible states in action having a positive probability. Okay, so no state action pair has a probability 0. So if you do that and you simulate enough episodes, then you're sure to eventually stumble on some episode for which any state action pair SA was used in the initial time point of the episode. Okay, so as the number of episodes tends to infinity, this guarantees that all state action pairs will be visited an infinite number of times. Okay, again, this is theoretical because you never have an infinite number of paths. Okay, but you can show that if all state action pairs have a non-zero probability for the first stage of the episode, then you're sure at some point to simulate them if you continue and continue and continue simulating episodes. Okay, so this you might say, okay, this solves our problem. Then we can estimate systematically q pi SA for all combinations of state S and action A, but there are problems associated with this method. Okay, so the first problem, so we said earlier that you impose to select the initial state and action randomly on the first stage. So this is possible if you simulate your Markov decision process with simulation. Okay, so if you have a simulation to generate your episode, then this is not very problematic. However, sometimes the episodes are generated not by computer simulation, but instead they're generated by actually interacting with the real environment. Okay, so you really make your robot walk in practice and see what happens. Okay, so in this case, you when you interact with the environment to obtain experience and generate episodes, you might not always be able to control the initial state. Okay, so in that case, it might be impossible to do exploring starts because sometimes it's impossible to say, hey, I'm going to start in state S. The initial state S is just the current state of the true environment on which you don't necessarily have control on. So this is one problem. And another problem, which is very serious, is that exploring starts, they are very, very computationally intensive if you have a large number of states and actions. Okay, because not only you need to have episodes for many state for all starting in all state action pairs, but you need many of them. Okay, because if you have only one or two returns to average to get estimate of the value function, this is not good. Okay, so the value function is the expectation of a return starting in a given state action pair. So to estimate an expectation, you need to average multiple rewards, not only 2 or 3, okay, but many of them if you want to have good estimates. So in practice, exploring starts is a poor solution to the problem we just outlined because it takes too much time and sometimes it's not even feasible if episodes are generated by interacting with a true environment instead of through computer simulation. So, an alternative that we could contemplate, which might be better, is to consider stochastic policies which continuously explore. Okay, so instead of exploring only at the first stage of the various the various stages, you could have possible exploration on all time steps. Okay, so for example, if you follow an epsilon greedy policy, you at every time you make an action, there's a epsilon probability that you will randomly sample some action. So this will force every state action pair to be observed eventually in your data set. And because you explore not only at the first stage but in all subsequent stages, this should increase the procedure because you'll face many more occurrence of state action of the state action pair you desire across the paths. Okay, so the epsilon greedy method is good. For now, we will stick with exploring starts. Okay, but eventually we'll discuss alternatives in this chapter. Okay, so as we said, exploring starts in practice, it's not the best idea, but for the purpose of studying and understanding what we're doing, it's a very convenient way to explain. Okay, so for now we'll stick with that, but eventually we'll see better methods. Okay. So up to now we discussed Monte-Carlo methods for a fixed policy. Okay, so we have some policy pi and we showed how to estimate based on Monte-Carlo simulations the state value function and the action value function for some fixed policy pi. So next what we'll want to do, we'll want to generalize these algorithms to allow refining your estimate of the policy to continuously improve on your policy. Okay, so this is called the control problem. Okay, so the problem where you evaluate the value function for a fixed policy pi, it's called the evaluation problem, whereas the problem where you optimize your policy at the same time then refining your value function estimate, this is called control. Okay, so control is when you not only refine your value function estimate, but you also simultaneously optimize your policy. So the idea we're going to follow here is similar to what we discussed in chapter 4, in the sense that we're going to have some form of generalized policy iteration procedure. Okay, so again, as in chapter 4, as in the GPI or generalized policy iteration procedure from chapter 4, we're going to constantly try to refine our policy, and every time we refine our policy, we'll try to uh, refine our estimate of the value function to better match the one of the current policy. Okay, so again, this leads to an iterative or recursive procedure, which leads to a sequence of value function estimates and policy estimates. Okay, so again, as we did in chapter 4, we're going to alternate between steps which are analogous to policy evaluation, where we refine our current estimate of the value function to have it better match the current policy by I. And then there are other steps which are analogous to policy improvement, where we take our current policy pi and we in fact take its associated value function, and then from that value function we try to get a new policy pi which improves on the previous one. Okay, so for the purpose of policy evaluation, we're gonna and within this GPI, we're gonna use the same idea we had earlier. Okay, so let's say we have our current estimate of the policy pi I. Then what we want to do, we want to find vi, which is approximately equal to the value function associated with that policy pi I. Okay, so to get an estimate of the value function, we're just going to apply what we discussed earlier. Okay, so we generate multiple episodes with policy pi I, and then for all state action pairs, we can find the associated returns across the various generated episodes, average all such returns, and this should give us an estimate for the action value function of some given state action pair, SA. And we do that for all state action pairs SA. Okay, so when we have a given policy pi I, we already know how to estimate its value function. Okay, so if we did that, the question is, how many episodes do we have to simulate? Okay, so in theory, if we used an infinite number of episodes, and if we use exploring starts, which means we're sure to find episodes where well, for every state action pair, we're sure to find some episodes where that state action pair appears. Then all such state action pairs will be encountered an infinite number of times, and for that reason, through the law of large number, we would have a perfect estimate of the value function, well, the state value function v pi I and the state action value function q pi SA. Okay, so if we were able to simulate an infinite number of episodes, then we would have perfect estimates. The estimates would match the true value function. And then once we have the true value functions, we can rely on the policy improvement theorem from the previous chapter, which said that we can select or determine a new policy pi I plus 1, which involves finding for each state S the action maximizing the action value function in that state S. Okay, so here we start with pi I. We simulate an infinite number of episodes to obtain the value function for pi I, and then we get pi I plus 1, the new policy, improved policy, by in each state maximizing, finding the action which maximizes the action value function. Okay, and we can do that recursively, so we get a new v pi I, pi I plus 1, then v pi I plus 1, then pi I plus 2, v pi I plus 2, by I plus 3, etc. And eventually, doing that through the policy improvement theorem, the policy will monotonically improve until you achieve convergence, and when you converge, you obtain the optimal policy. Okay, so eventually, so in this framework, uh, the algorithm is sure to converge. However, in the previous algorithm, we relied on an infinite number of episodes. In practice, this is impossible, so only a finite number of episodes can be generated. Okay? So, what happens in this case? So, what we could do, we can use a similar idea to what we did in chapter 4, where we introduced the value iteration procedure. Okay, so in that procedure, in the policy evaluation step of the GPI, instead of having an infinite number of iterations to get a perfect uh, estimate of the value function, we could only truncate that part where instead of having an infinite number of iterations, we can simply have a finite number of iterations. Okay, so maybe 10, 20, or something like that. And the limiting case was a single iteration of policy evaluation. So in the presence of a single iteration, the algorithm is called was called the value iteration. Okay, so here we could do the same thing. Okay, so in the policy evaluation step, so when we have the policy pi I and we want to estimate its value function based on Monte-Carlo approach by generating episodes, so instead of having an infinite number of episodes, we could a first approach would be to have a finite number of episodes, but a very large number. Okay, so if you have a very large number, you don't have a perfect estimate of the value function v pi, but you have a good one. Okay, and you could also, if you, for those who did Monte Carlo simulation classes, you can, let's say you have many episodes generated. Not only you can approximate the value function, but you can derive confidence bounds on this value function to see if your estimate is likely to be precise or not. So this is okay, this is nice, but to get sufficiently tight bounds in practice, you probably need many episodes. So this again might be too long if you have a large problem with a large number of states and actions. So in practice, generating many episodes in the policy evaluation step would require too much time, unless you have a small problem. So the second approach is, instead of having many episodes for each policy evaluation, you could instead have a few episodes, or at the limit, a single episode of policy evaluation before going into the policy improvement step. Okay, so exactly as in the GPI procedure we studied in chapter 4, you alternate between policy evaluation, policy improvement, policy evaluation, policy improvement. But every time you make a policy evaluation, instead of having an infinite number of episodes, you will stop after a few episodes. So you will just slightly refine your estimate of the value function. You won't move all the way to the perfect estimate, because moving all the way to the perfect estimate would take too much time. Okay, so in this case, we say the policy evaluation step is truncated. Okay, so what this means is, if we do that, we're happy with the value function only slightly moving towards the true value, not all the way through there. Okay, so this is analogous to value iteration from chapter 4. You do a single pass or a single sweep of states within your well, this is in chapter 4. So in chapter 4, for the value of iteration, you did a single sweep of states in your policy evaluation to get your new estimate of the value function, and you stopped after a single sweep. You didn't do some more. Okay. So doing that, we're ready to propose our first like official Monte Carlo algorithm to try to estimate the optimal policy for a Markov decision process based on Monte Carlo simulations. Okay, so the algorithm which is proposed in the textbook and which we will repeat here is a first visit Monte Carlo version of the policy iteration process with exploring starts. Okay, so what's going to happen? Um, we're going to apply the generalized policy iteration as we said earlier, but every time we generate episodes, we're going to use exploring starts to ensure that all possible state actions will eventually, state action pairs will eventually be encountered. And across all the episodes generated, we're going to pick a first visit approach where we only consider returns associated with the first visit to a state action pair in a given episode. Okay, so the algorithm will be presented in the next slide, but for now, let's just introduce the notation we're going to use next. So for any state S in the set of states and any action A in the set of all possible actions in state S, we define the following. So Qi is the state action value function estimate after episode I. Pi I is the current estimate of the optimal policy after episode I. So here I always stands for the episode. And ISA is the number of returns which were averaged to get the estimate of the optimal state action value function after episode pi. So the estimate of Q star SA is simply Qi. Okay, so Qi is our estimate of the action value function. So SIT and AIT are respectively the state and action encountered at time t and episode I, and ti is the termination time in episode I. Okay, so we're only going to consider episodic tasks here, which are certain to terminate at some point. Okay. So the Monte Carlo algorithm we just promised one slide ago goes as follows. Okay, so the first thing you do to start the algorithm, you initialize all your variables. Okay, so your initial policy, you take care of any policy. Okay, so for any state S or for all state S, you assign randomly or in any way an associated action pi 0s. The 0 stands for the initial algorithm of your initial estimate, of your policy. So for any state S, you assign it some given action pi 0s, which is the action selected by the initial policy in that state. The initial estimate of the action value function for any state action pairs is set to any real value, so you can put them all to 0, which would make sense. And then N0SA, the number of times each state action pair or the state action pair SA was sampled in the past to construct an estimate. Of course, it starts at 0 because initially you've averaged nothing to get your estimates. Okay, so you initialize all such variables, and then you do the following procedure. Okay, so you repeatedly generate episodes. So episode I for I goes from 1, 2, 3, 4, 5, and you go on and on and on until you're tired or until you don't have time or whatever. And you proceed as follows. So the first when you generate episode, we said we use exploring start. So the initial state in that episode I and initial action in that episode I, they are randomly selected such that all state action pairs have a non-zero probability of being selected. Okay, so this will force that every state action pair should eventually be encountered. Okay, so starting from the initial state action pair, then you can generate the whole episode of the Markov decision process. So you start in that state action pair, then you get a reward, then get to the next state, select an action in the next state, get a reward, etc., until the termination of the episode. And the actions here are selected using your current estimate of the optimal policy, which is pi I plus I minus 1. Okay, so every time you generate an episode I, you use the current policy estimate pi I minus 1. So once you've generated a new episode, then what you can do here is for all stages or all time points in the episode, you can calculate the return, okay, the sum of all discounted rewards starting at time t until the termination of the episode, and then you do the following. Okay, so if for every time t, if at time t it's the first visit, so you consider let's repeat that. So for every time t in the episode I, you calculate the return, and if it's the first time the state action pair STI and ATI is visited in episode I, then you're gonna increment or refine the action value function estimate for that state action pair. Okay, so if at time t the state action pair has been encountered in the past, you do nothing. But if this pair is encountered for the first time in your episode, then you do the following. So ni of your state action pair is ni minus 1 plus 1. It means that you're going to consider one more return for this state action pair to come up with the estimate of the the action value function for that state action pair. And then you refine your estimate of the state action pair as the following. Okay, so here, this is your current return, plus here, this is a fancy way to say that this is the sum of all other returns in previous episodes you obtain in state S, and take faced state action pair SA divided by NI SCA. So this is just NI minus 1 plus 1, as we wrote here. And this formula is just, so it might look complicated, but it really isn't. So you have a formula where x bar n, so the average, sample average of the first n observation is xn plus n minus 1 x bar n minus 1. So the sample average of the first n minus 1 values, and all this divided by n. Okay, so here it's the same idea. So at the nth time you face the state action pair STI ATI, then your current estimate is equal to the return you face right now, plus this is analogous to n minus 1. It's the number of times you face the state action pair in the past, okay, times the previous estimate. So the previous estimate is kind of x bar n minus 1 divided by n. Okay, so this is this guy incremented by 1. Okay, so this is how we get this new estimate here. So that's it. This is how the textbook at least proposes to try to find the optimal policy of a Markov decision process based on a Monte-Carlo algorithm relying on exploring starts. Okay, note that okay, we're not over yet. Okay, so here this is the policy evaluation step. Sorry, I kind of said it's over too quickly. Okay, so this is just the policy evaluation step. Then a quick note. So for all state action pairs SA that were not visited in episode I, then the estimates of the estimate of the action value function remains the same than before the episode was generated, and the number of time the state action pair SA was sampled in within the average, it remains the same also. Okay. So then this, okay, so we've generated an episode I, then we refine our value function estimate based on that episode. So it's kind of a policy evaluation with a single iteration here. And then once we did the single iteration of policy evaluation, where we hopefully pushed the value function slightly towards the true value function of policy pi I, then we can apply policy improvement where we select and we determine a new policy by telling the agent that every time you face a state S, you should pick the action which maximizes our current estimate of the state value function. Okay, so here, if this QI, this estimate was exactly Q pi I, the true value function for policy pi I minus 1, the true value function for policy pi I minus 1, then this would be certain to improve your policy. Now, because this is an estimate, this is not the true value function for pi I minus 1, that might, in some cases, maybe decrease the policy, but hopefully it will often improve it instead of lessen its quality. And then, once again, for all states that were not visited in episode I, your estimate of the value function, or sorry, of the policy, optimal policy, will remain unchanged because this function QI, it didn't change. Okay, so as we said here, if a state S was not visited, then the associated action value function estimate won't change, and because of that, this quantity won't change, so the policy for that state, the action selected in that state won't change. And then we're really done. Okay, so this is our algorithm, well, the algorithm at least which is proposed in the textbook to try to identify the optimal policy based on the Monte-Carlo algorithm. Okay, so for those who enjoy pseudocode instead of more formal math, I've copied the pseudocode from the textbook for this algorithm. Okay, so I won't go through it because it's exactly doing the same thing we just outlined, but maybe the language here might be more convenient for you if you have a more computer science background or something like that. So I've copy pasted the pseudocode, so feel free to have a look at it to gain a better understanding of what we just did. Okay. So one quick detail here. So while this process goes on, every time we generate a new episode, then for this new episode, the policy used in that episode has been changing. Okay, so the policy optimal policy estimate after one episode is different from the one after two episodes, different from the one after three episodes, etc. All this because of the policy improvement step included after each episode that is generated. Okay, so because of that, we average returns. Okay, when we estimate the action value function for state action pair SA, we average many returns associated with that state action pair SA. But contrarily to what we had earlier when we simply did policy evaluation, Now, the returns are not, first, they're not identically distributed because the policy changes over time. So the next actions and states that are encountered will change through time. Their distribution will change through time. So across the episodes, the various returns associated with the same state action pair will have different distributions. And moreover, not only they don't have the same distribution, they're not independent neither. Okay, because the outcome of an episode will influence your next policy estimate, which is used to select actions in your next episode. So clearly, there is some dependence in the between the various episodes. So when we estimate the state action value, the action value function, we are averaging returns that are not independent and not identically distributed. Okay, so contrarily to what we had earlier, where in the evaluation problem where we had a fixed policy, now we cannot invoke the law of large numbers for ID observations to ensure convergence of our estimate of the state action value, the action value function. Sorry. Okay. So what we know here is that it's impossible for this procedure to stabilize around a non-optimal policy. Okay, so what do we mean by that? It's impossible that this algorithm has a policy estimate which will converge to some policy pi, which is not the optimal one. Okay, because if that was the case, then eventually the algorithm would keep on simulating episodes from that policy pi, and by keeping on simulating from that policy pi, you would have a perfect estimate of the value function for that policy pi. So and when you do have this perfect estimate, then you can apply policy improvement and you're certain to find a better policy. Okay, so this just contradicted the fact we said the algorithm would stabilize around a non-optimal policy. Okay, so we know this algorithm can never converge to a non-optimal policy. However, according to the textbook, it was never proven by nobody that this type of algorithm would converge to the optimal policy. Okay, so we don't know yet. It might be possible that such algorithm would have a policy estimate which would continuously fluctuate around various policies and would not converge exactly to the optimal policy. Okay, so this comes from the fact that, as we mentioned, using this algorithm we just outlined, we average returns which are not independent and not identically distributed. So our estimates of the value functions might not converge and we might have infinite oscillation. Okay, so this, according to the textbook, we don't have an answer to this question yet. We don't know if the algorithm we presented converges to the true policy with probability 1. Okay, so if somebody was able to prove or disprove that statement, or the convergence or non-convergence of this algorithm, it would be very important, okay, for practitioners of reinforcement learning. Okay, so this was back when the last edition of the book was written. I don't know if somebody did it by then, but to the best of my understanding, this hasn't been solved yet. So one thing, probably, if I remember well, the textbook mentions that although this convergence was not proven in general, for some particular cases or some particular problems, you can have results about this, but there's no general result for general Markov decision processes. Okay, so we're gonna stop here for this video. So in the next video, we're gonna discuss approaches to avoid the exploring start, which we deemed inconvenient in that video. Okay, but this we will see, discuss this in the upcoming video. So have a nice day and take care.